This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
The first talk this quarter was by Vince Cerf, one of the designers of TCP/IP, which could have given us reliable and accurate communication over an unreliable channel. Clearly that hasn't been enough because almost all of us take some measures to protect our computers from the internet, whether it's using a Mac, Linux, or some obscure browser. I favor Lynx myself. Lots of this corruption actually comes from the channel, which seems sort of unnatural. The channel should at least be neutral in the discussion. Today's speaker, Charles Reis, will tell us about his work to address some of these issues.
Okay, thank you, Dennis. I'm Charlie Reis. I'm a PhD candidate at the University of Washington, and I'm going to talk about our work at UW to make it safer to browse the web. And I'm going to cover two main topics in this talk. The first is that we've seen that some web pages are being modified in flight, that is, between the server and the browser, and some of the dangerous consequences that can come as a result of this. And we're able to detect this with a tool that we call web tripwires. Second, I'll give you an overview of our ongoing work to try to design new browser architectures that make it safer to run all the active code that's on today's web. Okay, so our work is motivated by the fact that it really isn't safe to browse the web today. And you can see this in a pretty typical browsing scenario, where you might have several windows open in your browser, including some to websites you've been to before, like a webmail client or renting movies on a site like Netflix, and then the other sites you haven't been to before, like some new search results that you have just looked up. Now, there's a lot of bad things that can happen in these situations. So first of all, one of these malicious sites, one of these search results could try to install malicious software on your computer by exploiting a vulnerability in your browser, and in so doing, be able to run arbitrary code on your machine. Now, you've probably seen a lot of this in the news. There's a lot of cases where this is happening in practice, where people are hiding exploits in banner ads and on websites to try and get people to install the software on their computer. Now, unfortunately, this is far from the only problem that we see on the web today. You may have also heard of cross-site scripting attacks, where an attacker has the ability to place their own script code on someone else's web page. And this lets them do things like steal cookies or modify the contents of the page, effectively control someone else's web page. In fact, Yahoo Mail was vulnerable to a cross-site scripting attack in 2006 that allowed an incoming email to your mail client to run script code as part of the mail client. And so this let a mail send mail to other people in your address book and then send spam to spread itself as a worm. Now, there's also what are called cross-site request forgery attacks, which abuse the way that browsers handle credentials on sites. So if you're logged into a site like Netflix, Netflix places a cookie on your computer so it identifies you on future requests. Well, another website in a different window in the browser could also send a request to Netflix's server, and your browser will tack on those same cookies because it's going to the same location. Now, if sites don't take steps to prevent this from causing problems, then that becomes a vulnerability. And in fact, Netflix was vulnerable to this vulnerability, to this sort of exploit in 2006. So other sites could modify your account settings just in the case that you were logged into Netflix at the same time you visited them. Now today I'm going to focus mainly on what might be an emerging threat, which is that when users visit a website, they might not get what the publisher intended, but they might get some altered version of that. For example, an ISP might have injected an advertisement or some other code into the web page, which changes what the user sees when they visit the page. So in this talk, I'm going to focus mainly on that last issue of in-flight page changes. And I'll talk about our measurement study that shows that this is happening in practice and that it can have some serious consequences. And then we can detect it with some JavaScript code that we call web tripwires. Then I'll step back and show how we might be able to address some of these other threats by actually changing the way that web browsers are architected to deal with the fact that there's lots of active code on today's web. And that's ongoing work at University of Washington CSD department, so I'll just give you a high-level overview of that. OK, so the first topic is the in-flight page changes. And this is a measurement study I've done with Steve Gribble and Yoshi Kono at the University of Washington and Nick Weaver at the International Computer Science Institute. This is work that will appear at the NSDI conference next month in April. OK, so we were inspired to do this measurement study based on a news article we saw last summer that said that some ISPs might be injecting ads into the pages their users are requesting. And we were pretty surprised by this, because this means the ISP actually had a box on their network that was doing some form of deep packet inspection, looking at web pages, analyzing their contents, and then modifying them to inject code into them. So we were pretty surprised that ISPs would actually go that far as to modify this traffic. So we set out to answer the question, OK, how often is this actually happening in practice? So I'll show how we were able to detect these changes, what we found in our study, some of the dangerous consequences of the changes we did see, and then what publishers can do about it. So we realized we could detect a change like this just by putting JavaScript code on our own web page. So we call this a web tripwire. It's just a piece of code that looks for changes to a page. And the idea is we'll put this JavaScript code on our own web page, and when a client requests the page, that code runs in their browser. It then compares the HTML code that the client received to what we expected it to be, effectively using a checksum. And if it's different, say if an ISP had injected an ad into the page in flight, we'll see that difference in the HTML, and we can display a message to the user saying this page has been modified in flight. Here's what the difference was. We'll also report the change back to our server so we can analyze it later. Now we have this online at vancouver.cs.washington.edu on our website there. And I'll leave this URL up there for the rest of this part of the talk. You're welcome to visit it anytime you're on a network that you think might be playing with your web traffic, just to put it to the test. But I'll talk a little bit more just about how web tripwires work. In general, we've built it so that they can be added to any web page without interfering with the way the page works. And the idea is the client would first fetch and render the original web page. And that has a single line of JavaScript, which fetches a second JavaScript file that includes the contents of the web tripwire that has the logic for the tripwire. And it also includes a second encoded copy of the page. Now, you could send along a checksum if you wanted to save overhead. We sent along a whole second copy of the page as a string, so we could do an easy comparison if we found a difference. And then the tripwire will just compare that encoded copy with what the client received, and will report if there's a difference. Now, there's a slight catch here, which is that you can't just ask the browser for your own HTML source code. What it will give you is a pretty printed version of its internal representation. And of course, every browser reports this slightly differently. So we have to do a little trick where we send an XML HTTP request, just a request for our own document, and get it back as a string. And because the page is already cached in the client's browser, this doesn't even involve a network request. We just get back our own contents as a string, and we can do that comparison. OK, so that's how it works. Now, to use this in a measurement study, we wanted to get lots of people to come visit the page, especially lots of people on different networks, so we could see if different networks were doing different things to the page. So to get a large audience, we thought, this might be something that Slashdot could help us with. So we posted the story to Slashdot, to Dig, to Dave Farber's Interesting People list, and so on. And that worked out pretty well for us. We got about 50,000 unique visitors to the page over the course of about 2.5 weeks. So we had a nice large data set to work from of, in all these different networks, is our page being modified in flight? OK, so what did we find in our study? I mean, honestly, we would have been surprised to find pretty much anything. We didn't really think it would be modified that often. As it turned out, we saw 657 clients report back some change to us. And that was about 1.3% of the visits to our page. So that was a lot more than we were expecting. Now, as it turns out, many of these are made by software that's installed on the client. Proxies that are doing things like pop-up blocking and ad blocking. Now, these are not browser extensions, but rather proxies that are installed outside the browser that change the page before it gets to the browser. We also did see changes that were made by agents in the network, things like ISPs and enterprise firewalls. And what's more, we found that there was really a diverse set of incentives for why people would want to modify the page between the server and the browser, and that these incentives weren't always in line with the goals that a publisher might have for its own web page. So for that reason, publishers might want to know when these changes are being made to their page, so then they could take some steps to react to that. So to give you a sense of what these changes were, I'll walk through a few of the major categories that we saw. And these include changes made by internet service providers, enterprise firewalls, proxies installed on the client, and even some cases of malware. OK, so the first category of changes that we saw were changes made by ISPs. And a common type of change was, in fact, injected advertisements. This accounted for about 2.4% of the changes that were reported to us, which means about 16 IP addresses reported this. And this was often done by companies like Nebuad that contract with smaller ISPs to inject JavaScript code into every page that users request. Now, this code will do behavioral tracking. And so Nebuad knows where you've been. And then they can inject advertisements that are targeted to your browsing history based on that information. This is also done on some free wireless networks like MetroFi, which is in this area, Lockbox, and some others that support their wireless network by showing you ads embedded in the pages that you're visiting. They are actually modifying the pages themselves to show you these ads. OK, now from the ISP's perspective, there's clear reasons why they'd want to do this. They get to make money off of people browsing the web through their pipes. On the other hand, it might annoy users. It might detract from a publisher's own advertisements. So publishers might want to know when this is happening. Now, the other disturbing thing is that we viewed this as it might be a growing trend. In fact, we've seen several companies after the study that also seem to be advertising the service to ISPs. So there's companies like PerfTech, Front Porch, Adzilla, and a company called Form that's been in the news recently for having some major contracts with large ISPs in the UK to do this same sort of service. So we may be seeing more of these in-flight page changes in the future. Now, this isn't the only thing that ISPs were doing either. We also saw some cases where ISPs were compressing the page in some way or another to try and reduce bandwidth on low bandwidth networks like cellular networks. An example of this is image distillation, where they will take the images on a page and first ship the clients a low quality version of the image to save bandwidth, and also inject JavaScript code. So if you click on one of those images, you can then request a full copy of the image. So these sorts of changes were also being made to our page, accounted for about 4.6% of the changes that we saw. The next level, we did see changes being made by enterprise firewalls. And these were interesting because these might be something you might want to allow in some cases, as they're designed to improve the security of browsing the web for the enterprise. And these are done by products like Blue Coat Web Filter, which will inject JavaScript code into web pages to look for malicious behavior on the page. And this might be things like a page trying to disguise what's in the location bar, or trying to do other shady practices that might be associated with phishing. So it's doing some heuristics to see, is this page behaving in a strange way? Now, from the enterprise's perspective, this is nice. It might protect their clients from certain risks. And from the publisher's perspective, it might also be nice to know if these checks are being done, because this means that that client is in a well-protected environment. So if you're interested in assigning risk to certain clients versus other clients, you may want to know, OK, this client is in an enterprise with security checks versus another client which is in a free wireless network having ads inserted. And you might treat them with slightly different risk levels. OK, now most of the changes we saw, about 70% of them, were done by proxies on the client that were designed to block pop-ups or ads or other annoyances. And these were done by some personal firewall programs like Zone Alarm and CA Personal Firewall, whose normal job is to usually block connections on certain ports. But as it turns out, they're also injecting code into web pages to prevent pop-ups and some other annoyances. It also was done by some dedicated products like AdMuncher and Proxometron, which advertise themselves as being able to block annoyances on the web, like ads and so on. Now, from the client's perspective, this might be nice because it could make certain pages less annoying. They have lots of distracting flash ads and pop-ups. From the publisher's perspective, obviously, you might want to know if your ads aren't being viewed, so you can account for that. So a final category that we were sort of surprised to see is that we could detect certain types of malware on the client's machine that were modifying web pages before they got to the browser. And for example, one client had adware installed, and this was modifying our page to show ads. Now, when most people visited our page, they'd see a frame that had something like this, which is just a set of text and some links. And what this client saw was a little different. There's a few extra links on that page, and those links have double underlines. And I'll highlight those in red. Now, if you put your mouse over one of those links, it'll pop up a new frame with ads that are targeted to whatever that word was. And so this is a pretty invasive change in terms of the source code of the page. It's going through and turning things into links and adding lots of JavaScript code. We also saw two clients that were affected by worms that appeared to have received our page with an exploit injected into the top of it. Now, our hypothesis is that these clients were affected by ARP poisoning, where there was another client on their local area network that was infected by a worm. Now, that client started sending out ARP packets that said, hey, I'm the router, send your traffic through me. So then other clients who requested web pages would go through the infected client, and that client could inject exploits into web pages to try and infect other clients. Now, as it turns out, we've also heard reports where this sort of attack may also be targeting server rooms, where even if your server is not infected and is well protected, if there's something on its local area network that is infected, it can inject itself between the server and the outside world, so it can inject exploits into web pages on their way out. So this is also a significant problem there. Now, obviously, these sorts of changes are just there to help the malware author, and either to make money off the ads or to spread the worms. So they're not something that we want to support, and it's clear that publishers might want to know when this is happening to their page. OK, now, all of the changes so far were made with some incentive. They were made on purpose, and they were accomplishing some goal. But as it turns out, they also had some dangerous consequences that might not have been intended. That there was some unanticipated impact, like breaking functionality on other pages. So for example, some of the changes we saw introduced JavaScript code that caused bugs in our web page that caused either our test to break or to not work quite properly. And we had to get feedback from users to say, OK, here's what happened. Some products that were doing this were some of the ISP compression changes and the CA personal firewall software. We also saw some of the changes that were interfering with popular websites like MySpace and a lot of web forums. So for example, you can find a lot of these on the web just by searching around. You might find some comments on MySpace or forums that have this little bit of pop-up blocking JavaScript code showing up in the comment itself. And this is because the user had CA personal firewall installed, and that was injecting pop-up blocking code into their web pages. But it happened to be injecting it in the wrong part of the page so that it showed up in the comment that the user posted to MySpace. So they end up seeing this extra code showing up in their post. And in fact, you could even find some posts of users saying, why is my computer doing this? I didn't put that there. And so they're very confused as to why this code is showing up. Now, unfortunately, it does get worse than this. We found that some of the in-flight page changes actually introduced security vulnerabilities into our web page. And here I'm talking about cross-site scripting vulnerabilities, where it would allow an attacker to put their own code on our page and run it to control the contents of our page. So this is significant because cross-site scripting vulnerabilities are often due to bugs at the web server. And it's something in the way the web program is constructed. And web developers put in a lot of effort to make sure that their sites don't have these bugs. Now, what happened here was that there were some proxies, AdMuncher and Proxometron, which were installed by the client to do things like ad blocking, that inadvertently made otherwise safe web pages vulnerable to cross-site scripting attacks. Now, I'll explain how this works in just a second, but I want to note two things about this. The first is that the web developer didn't really have anything that he could do about this, because the vulnerability wasn't introduced until the page had already left his server. But the other problem is that for the clients who had these proxies installed, these proxies were modifying most, if not all, of the web pages they were requesting, which meant that most of their web traffic became vulnerable to attack. Now, in the case of AdMuncher, this was many of the HTTP unencrypted pages that they visited, apart from a few that appeared on a blacklist. In Proxometron, there was even an option to have the proxy end as the endpoint for encryption for HTTPS encrypted pages, which meant that for anyone who had that feature turned on, every page they visited became vulnerable to a cross-site scripting attack. Now, if you view the web browser like an operating system where you're running lots of different programs from lots of different places, and suddenly every program becomes vulnerable to an attack, that's sort of analogous to a root exploit. And there's some really serious consequences that can come as a result of this. And I'll show you those in a minute. OK, so how did this cross-site scripting vulnerability work? Well, in the normal course of execution, these proxies would inject a piece of script code into every web page, or most pages, that was designed to look for ads and strip them out, or similar annoyances. Now, as part of that code, it happened to include the full URL of the page in a JavaScript comment or in a string or something like that. Well, the URL is something that an attacker can influence. So an attacker could construct a URL that was valid, but that had script code hidden at the end of the URL. And you could put that either after a question mark to treat it as a server parameter, or you could put it after a hash to treat it as some anchor tag on the page. And then the attacker would try to convince users to follow this URL. So they could do this either by sending them a phishing email or by redirecting the user from some other web page. And once they do that, the proxy will copy that URL into the page, and the browser will then run that script code as if it was part of the page itself. So this could be used for things like phishing attacks on banks. There's several banks out there today that have unencrypted front pages that are served over HTTP and have a login form with username and password. And they don't switch you over to HTTPS until you've clicked the submit button. Well, if we can run script code on that front page, then we can send that password somewhere else. But we've built another type of exploit that shows the danger of having this sort of vulnerability on essentially every page. So we built an exploit that would detect if a user was running one of these vulnerable proxies, effectively by using a web tripwire, seeing if it was modifying our page in a certain way. If so, we would redirect them to Google's homepage with a little bit of extra script code in the URL. So now we're running script code on Google, and we can modify the query form. So when the user types in a query, that would still go to Google's server, but our exploit code would propagate to the results page. So now we can control the results. We can modify where they're pointing, what they say about the sites, and so on. We pretty much control this page. But what we did is went through every outgoing link on the page and appended our exploit code to the outgoing links. This means that now any link that the user visits in this browser window is something we can also control and modify as we see fit. So we essentially own this browser window until the user types in a new URL by hand or closes the window. So this is a pretty serious exploit. OK, so the aftermath of these vulnerabilities, we have reported them in the cases that we found them, and they've been fixed. So if you happen to be using any of these proxies, be sure to upgrade to the newer versions. But they really demonstrate how much power this web page rewriting software has and the consequences that come up when something goes wrong in it. Also, I wanted to point out that the fact that we were using web tripwires did help us to find these vulnerabilities. We were able to look through the changes that were being made to our own web page and find cases where the URL to our page showed up in the change of what was being done to our page. So those were cases we could flag for further analysis to say, look, this is something the attacker might be able to control. Is it something that's exploitable? And so we think that web tripwires could help to look for these vulnerabilities in the future. OK, so now that we've seen what's happening, what can publishers do about this? Well, the first thing that comes to mind is probably just switch over to HTTPS. If your pages are encrypted, then they're not going to be modified in flight, and the problem will be solved, at least in cases that clients don't have a proxy that's acting as the endpoint of encryption. But you're also probably realizing that this isn't a practical solution in all cases. Do you have a question?
I was wondering if you measured whether that was successful in stopping these modifications.
HTTPS?
Yes.
We didn't measure how often it could prevent that. So if the encryption was happening from the server to the browser, then the modifications couldn't take place. It's actually interesting that HTTPS provides integrity guarantees for the client. They know that the page has arrived from the server intact, as long as they don't see warnings from their browser. but it doesn't provide any integrity guarantees to the server. The server doesn't know if someone else has acted as the endpoint and then given the page to the user. So we wouldn't see how often that would protect clients. Now, at the same time, HTTPS isn't always a practical solution because it can be very costly. You might not be able to switch every page on the web over to using HTTPS, just in terms of cost. And it's also rigid in the sense that it may prevent some things that you would like to have happen to your page. You might not want to prevent all these security checks, but in a simpler sense, you might also want to allow things like transparent caching in the network, or other things that rely on the open nature of HTTP. So in cases where you don't want to switch to HTTPS, we suggest that you could add a web tripwire to your own page. And again, this is just JavaScript code you add to your page that detects whether these changes are being made in flight. Now, the nice part about this is it's very easy to deploy. It doesn't change the way the page renders itself. It's just a check that's made in the background and that can report to the user or to the server when it finds something. And we've built a configurable toolkit to make this very easy to deploy. It's open source and it's on our website. And we've also built a version of this that's a service hosted on our own website. So someone could include this JavaScript file from our server on their own web page. And then any changes that were made in flight would get reported to our server, and we could provide reports to the publisher about what was being done to their page. Now, at the same time, this is not a cryptographically secure solution. This is something that if you had an adversary that was looking at the web page in flight and saw one of these web tripwires, it could disable it or it could try to make it look as if there had been no change. So it's not a perfect solution. But we do think that you can make it robust against many of these changes. So if you think that there's an adversary, you could try to obfuscate the way the tripwire works and make it difficult for them to automatically locate and disable a tripwire on the fly. To give you a better sense of this, I'll walk through some of the trade-offs between using HTTPS and web tripwires. So HTTPS will provide both confidentiality and integrity to your page. It will prevent in-flight page changes as long as it's making it all the way to the client. But it could also prevent some useful services like caching and like some of these security checks. Web tripwires will not prevent changes, but they will detect when they're happening, so you can analyze what's being done to your page, maybe react in other ways, like legal action against ISPs if they are doing very egregious things. And it will detect most changes to HTML, maybe not everything. For example, we won't be able to detect things like full page substitutions or interstitial pages, where our code just doesn't run at all. In terms of strength, HTTPS is cryptographically robust, where we may face an arms race if adversaries try to disable web tripwires. But we think that obfuscation can really be effective in this because the adversary would have to identify code that could be very easily mixed in with the logic of the page itself. Very hard to identify what the web tripwire is. And finally, in terms of cost, with HTTPS, you have to get a certificate that's signed. You've got extra computation overhead on the server that may affect your throughput. And you've got extra round trip times, which may significantly impact latency for some clients. Whereas web tripwires are very inexpensive to deploy. They just run in the background and report this change if they see anything. And we've measured some of the performance impact for our study. And we've built a web page and compared its performance to switching to HTTPS and switching to web tripwires. Now, we didn't use crypto hardware for this, which can accelerate some of these crypto operations, but that would introduce yet another cost for the servers. And we've seen that web tripwires impose low latency for the client, that in terms of the start latency, when does the page actually start loading for the client, we don't affect that at all because the tripwire is running in the background. And the end latency is increased by a small amount as the tripwire runs. Versus HTTPS, which requires extra round trip times to set up the SSL handshake. And that can impact the perceived latency for the client. And in terms of server throughput, where web tripwires affect the throughput far less than HTTPS because we're not requiring all sorts of CPU overhead to establish this SSL connection. In fact, we're just requiring some extra bytes to be sent for the tripwire code and that extra copy of the page to compare against. Yes?
Do servers currently use cryptographic hardware commonly?
Some of the larger enterprises will use this on sites that they want to have very scalable HTTPS services. I don't have numbers as far as how many sites use this hardware. OK, so just to wrap up this part of the talk, we've seen that web pages are being modified in flight for some fraction of users. It may not be a very large fraction right now, but if 1.3% is somewhat of an accurate figure, that may be large for certain websites with lots of traffic, and it may be a growing trend. We've also seen that these can have negative impact for the publisher, both for reasons that people are intending, like injected advertisements, and that they might not, like bugs and vulnerabilities, and that you might want to detect when these changes are being made using something like web tripwires. Yes?
Have you had any success in convincing publishers this is actually a problem? Like that they would go to the trouble of putting something different on their page if they care about it?
So I have given the same talk at Amazon and at Google, and they've expressed some interest, but I haven't seen any specific, OK, let's put this on our own web page. That may be something that could end up happening as a result. It might even be something that these sites could add in the background to their page for a one-day test to see, OK, does this validate for our site, and are there things that we'd be worried about? It'd be very easy to do as a test like that.
Question? Since publishers aren't doing it, what about users?
So users could try to do a similar check. This question was whether users could do this if publishers are not. The challenge is that the user would have to have some known good representation of the page. And so they would need to get this checksum or second copy through another channel that isn't being modified by the ISP. You could imagine a couple of ways that you could do this, either by having an HTTPS connection for your single check, or by going through other clients, or being multi-homed. But it's a much harder challenge for clients to get that second copy versus servers, which know in advance what that good copy is. Question?
Yes, the extra round trips are just at the beginning when the session is being established, right?
That's correct. The extra round trip times for HTTPS are just for that session establishment.
You said you collected visitors from different sources such as Dig and Slashdot, and did you see how like all the ad blocking people from Dig, because Dig has lots of advertisements, or did you look at any validation of that?
We didn't try to correlate whether users from Dig or Slashdot were more likely to have certain of these proxies installed. I can say that since our results tended to come from a fairly technically oriented crowd, it might be different for the full web population. There might not be as many people with pop-up blockers installed.
How easy it is to mount those ARP attacks that you talked about earlier?
That's a good question. I don't know how easy it is to mount the ARP attacks. I know that there are some attacks in the wild that are using this strategy, that are using, there's some worms called ARP iframe and so on that will send ARP packets to the local area network. I don't know how common these are or how easy it is.
But once you have found that there is a problem and you have detected someone is sitting and doing man in the middle by being an ARP attacker, what do you do next?
So the next step, if you've detected it, might be trying to notify the user that they're on a network with this happening, and to warn them, not to trust your browser. You might not want to use your browser at this point until you're on a safer network. It is theoretically possible that the worm could try to prevent those messages, but difficult in practice. And you may also try to identify, if you can, what network it is and notify network administrators.
Just last question. It sounds like if you were on a cable network, DSL version of their services, it is a big LAN. So anybody could mount ARP attacks on you. Or if you're on a big DSL network, anyone should be able to do an ARP attack on you by just sending a bunch of ARP packets. So anybody, therefore, whose IP address is known could become vulnerable to this attack.
So I'm not sure if that will work if these sorts of ARP attacks can be launched on cable networks. In particular, they rely on the translation from IP address to MAC address. So it's got to be on your local area network. And given that you're not using Ethernet to get to there, I don't think it would be an issue there. Another question?
Are ISPs the only sinners in this area?
Well, we've seen that there are enterprise firewalls in addition to ISPs.
Oh, I'm sorry, yes.
So there are parties along the way that are doing it, yes. So they're not the only parties.
Since you're interfering in quote-unquote business practices, did you get any nasty comments yet?
We have not had any contacts from the companies that are engaged in in-flight page changes. We were interested to see if some of them would try to blacklist our page and not modify it. We did see that some of the Nebuad changes appeared to change how they were modifying our page as the study went on. We're not sure if this was on purpose or whether this was a result of internal testing. There were visits from Nebuad's own IP addresses coming to our page, so we're pretty sure they were aware of us. OK, so let me move on to the second part of the talk, which is beyond these in-flight page changes, how might we deal with some of the other threats that are on today's web? And this is joint work with my advisors, Steve Gribble and Hank Levy. And so how did we get into this situation where there's so many threats to browsing the web safely? Well, we view one major reason of this as the fact that web content has evolved significantly since the early days of the web. So we used to just have static documents with text and images and links that you could navigate between them. So the browser could just be a simple document renderer that allowed you to navigate through these pages. But this has changed significantly since then. And we now have significant amounts of active code that are running within web pages, whether it's JavaScript code or Flash or Silverlight or other new formats. This is real programs that are running within the web browser, and the browser is acting as their runtime environment. And in that sense, the browser is really acting like an operating system for these programs, and it's got to keep them isolated and run them in a robust way. But unfortunately, today's browsers are still architected like document renderers, and they don't reflect the fact that they're running all this active code. And we've had to sort of bolt on security models and find all the cases where it's not working properly. So this has led to a lot of the safety threats that I talked about at the beginning of the talk. And so it's more than just things like in-flight page changes. Browser exploits are one problem, but we're seeing things like cross-site scripting attacks, cross-site request forgeries, even other types of interference between web pages and the browser that really we need better support for the fact that we're running real programs here and not just rendering pages. And we think that to get there, we're going to need to change the way that web programs are defined and the way that browsers are architected to reflect this fact. And so there's some long-term changes that need to be made to browser architectures. Now, in our Hotnets paper last fall, we tried to boil this down to a set of 4 architectural issues that we think need to be improved in today's browsers. And I'll touch on each of these before I conclude. The first one is we need to have better ways of defining what the boundaries are between these web programs. We also need to be able to prevent unwanted code from appearing within these programs. We need to isolate these programs from each other once they're inside the browser. And we need to be able to enforce uniform policies on what these programs can or can't do once they're running in the browser. So the first issue is trying to identify program boundaries on today's web. Now, a web program is not just a web page. It's a collection of pages that can talk to each other in the browser and interact. And of course, today's browsers use the same origin policy to try and say what pages can talk to each other and what can't. So if 2 pages from different origins, then they can't access each other. Well, we view this as a pretty fundamentally flawed approach for a program platform, and that it doesn't really match the boundaries that you'd want between web programs. And you can see this in all sorts of ways. For example, it's too narrow in some cases, where you want to create some sort of mashup between content from, say, MySpace and Google Maps. And the browsers today make that awkward to do safely because those are coming from different origins. So you either have to get around it by using script files or deal with the fact that they can't talk to each other. At the same time, the boundary is too broad as well, because you may have many independent web programs on a single site, like MySpace profiles, that you'd like to have isolated. But because they're all from the same server, they're all lumped into the same isolation box in the browser. And then there's the fact that it's not a very secure boundary to begin with. That work here out of Stanford in the last year has shown that DNS for binding attacks pose a significant problem for today's browsers. That an origin is just a name that's loosely bound to an IP address. So if you request a name like evil.com at one point in time, and that resolves to some internet address, you get a page from that server. And then it requests a second page, and your browser will again ask, OK, where's evil.com? And this time the server might reply, oh, it's some IP address that's on your local area network. And then your browser fetches that page and treats those two as if they were coming from the same origin. So suddenly that external site can start spying on your internal network. So that's a significant problem. So for these and other reasons, we think that we need better mechanisms for defining what the boundaries are between web programs. In particular, we need new abstractions in browsers and in the way websites are defined. We need an explicit abstraction for a web program. It just doesn't exist today. We're trying to infer this from the origin. And that's a set of documents and code and data that are resources that should be considered part of a program. They can be isolated from other programs. We also need an abstraction for an instance of that program within the web browser. And you may have multiple instances of the same program within a given browser. And that may be able to help you isolate other certain types of attacks. The important thing here is that we have ways to explicitly assign what belongs to what web program. And this is still an open question. We're looking at some solutions to this in our research, but we're not sure which way it's going to go yet. One approach you could take is to try to use asymmetric keys to try and identify a web program. So the publishers could come up with a key pair, and the private key would essentially be a secret that identifies the program. And to the client, the web program becomes the public key and a set of signed documents and code and resources that they can tell all belong to that program because they're all signed by the same author. Now, there's a couple of nice properties to this, which is that a single server could host multiple independent programs just by coming up with multiple key pairs. You could have one web program hosted on multiple servers by sharing that private key with servers you trust. And you don't necessarily need a PKI for this, because you're not trying to say who's giving you this web program, just that this web program is distinct from another one who doesn't have my private key. Now, whether this can be done in an incremental way, that there's certain web programs you want to enforce this boundary and everyone else can rely on origin, and whether this is a solution that will work in all cases is still open. We're still looking at that. We think this may be one promising approach. Second, we need to be able to prevent unwanted code from running within a web program once we know what the boundaries are. And again, here cross-site scripting attacks are a perfect example of this. In today's web, there's lots of ways that attackers might be able to put their own code in your web program, say by hiding things in the URL or by posting certain things to your site that get stored in a database and are later reflected to users on the page contents. So they're putting their own code on your page. But even if you could fix all of those problems, we've just seen that in-flight page changes are also injecting active code into web pages. In fact, in our study, 90% of the changes that were reported to us involved injected JavaScript code. So most of the changes being done are active code being injected into somebody's web program. And as websites become more like web applications, as you deal with things like Gmail and map applications where there's lots of code running, this active code can really interfere with what's going on and can interact in unanticipated ways. So this means that publishers really don't have control over what code is running in their program. So it's very hard to reason about what it's going to be able to do. So we think it's important to be able to authorize what code is allowed to run in your web program, at least in cases where the web program is actually running as an application that you want good protection on it. And there's ways you could do this. We've looked at an approach called whitelists for scripts. And there's some work that appeared at www from AT&T in Maryland on the Beep project that looked at this. And we were doing some concurrent work at the time to try to identify, OK, here are all of the scripts that are allowed to be on a page. And the publisher would then provide a whitelist that would say, OK, here's a hash for every piece of JavaScript code that's allowed to run on my page. And if the browser encounters a piece of script code on the page that doesn't appear on the whitelist, it should ignore that. So we now have an exhaustive list of everything that's allowed to run. And in terms of cross-site scripting attacks, it's much harder to get something injected into that whitelist than the rest of the page. And in terms of in-flight page changes, you may be able to sign this whitelist if you're using something like key pairs for identifying program boundaries to say, look, here's the authoritative set of code that's allowed to run in my program. Now, you'd want to generalize this as well So it applied to all active code, not just JavaScript. So an injected piece of Flash code might be just as bad as an injected piece of JavaScript code. So you want to generalize there. Now, of course, there are some challenges here for dynamically generated pages, where if the script code is being generated by the server as the page is being shipped to the client, you might not know all of the script code in advance. And that's done on a lot of popular pages today. And so we've done some work at looking at, OK, how could you address this situation? Possibly by signing these certain snippets of code, possibly by saying, OK, in some cases, we're just going to trust them. But we think you can get to a place where you can support these dynamic pages as well. OK, even if you could solve these first two problems of defining what the boundaries are and and preventing unwanted code from appearing within them, you may still have problems where programs interfere with each other in the browser itself. And there's a couple of ways that this could happen. First, there's cross-site request forgery attacks, where if I'm logged into a site like Amazon in one part of the browser, and it has cookies on my computer, another site sends requests to Amazon, and that has my cookies. Now, really, there's no reason that that site should be able to use my credentials, but current browsers don't make a clear distinction between these different instances. And then there's issues of resource contention and failures that aren't isolated between web programs. So if one web page is using the CPU heavily or using lots of memory, that could make the whole browser unresponsive, including other pages you're visiting. And if a crash occurs in the rendering engine, suddenly you've lost all the pages you've been using. So if you view this as an operating system, this is sort of like being back in the days of DOS, where we didn't have good isolation between programs. And we can really do better than this. We can do a better job of isolating credentials between web programs. And if we know what a program instance is, we can say that, OK, I'm logged into Amazon in one instance. And if another site tries to send a request to Amazon, that's creating a new instance. It doesn't get my same credentials that my authenticated instance has over here. And in terms of robustness, we already have a great mechanism for this. We have processes in the operating system. We should be able to reuse parts of the operating system that are relevant here and put different web programs in different processes so that when one crashes, it doesn't affect the other sites I'm visiting. And we can put the browser's user interface in a separate process so that can outlive any failure. And so then we'll have a much more robust way of handling these web programs. And we have a tech report online that shows how you can do this in today's browsers without breaking backwards compatibility, even though it's a bit harder to identify the boundaries between web programs, just in terms of the way security policies work. OK, finally, we think that you need ways to apply uniform policies on what pages can and can't do to your computer and on the network, regardless of what type of content they have. And you can see this if you take just a stock web browser and a web page with some JavaScript on it. You probably have a fairly good conception about what that page can do to your file system or to the network, at least if there's no bugs in the system. But as soon as you start installing things like Java or Flash or Silverlight or other plugins, all bets are off, because each one of these things has its own security model, and it interacts with active code from the web the same way that pages do within the browser. And what's worse is not only might these environments have bugs, but even if those are all fixed, there are subtle differences between these runtime environments that mean that when you start composing them, pages can do things that they couldn't do with any one of the environments in isolation. And actually, the DNS rebinding study here was a good example of that. That some of these DNS rebinding attacks become easier when you combine JavaScript code and Java code, because they have different ways of doing these DNS requests. So suddenly, by combining these environments with different security policies, you become more vulnerable to attack. Now, unfortunately, the same thing happens with browser extensions. If you install things like GreaseMonkey or AdBlock into Firefox, those can also defeat the browser's security model. In fact, GreaseMonkey had a vulnerability in 2005 that allowed web pages to subvert the same origin policy by going through GreaseMonkey's own code to then access the network. So at that time, there were effectively no boundaries between pages, no boundaries between origins within the browser. So that was a significant vulnerability. And GreaseMonkey had to be careful to fix this, that there was nothing in the browser's own security model that would prevent this sort of thing from happening. And so when this is the case, when plugins and extensions can throw out the security model, there's really no way to reason about what a web program can or can't do to your computer. So we took a first cut at this problem with the Browser Shield project at Microsoft Research. I was working on this as an intern 2 years ago, where we were trying to create an interposition layer for JavaScript code for browsers. And our goal here was to prevent exploits of known browser vulnerabilities. So we could look at what a web page was doing in JavaScript and say, if it's about to exploit a vulnerability that we know about, let's prevent that from happening. But it actually gave us a pretty nice policy framework to say, OK, JavaScript can do these actions and can't do these actions. And we could define policies that would enforce this. Now, the way that we built this happened to be an in-flight page change. Like the Blue Coat web filter, we deployed this at an enterprise proxy that would rewrite pages in flight to allow us to have this interposition layer in JavaScript code. And that had some nice properties for deployment. It meant that we didn't have to install things in everyone's web browser to get this protection. But it also meant there were some real challenges for us. Obviously, it made it hard for us to address HTTPS pages if they were encrypted. It was hard to address other types of active content that might not have been as easy to rewrite as JavaScript. And JavaScript wasn't that easy to begin with. And importantly, it was hard to address things like browser quirks, where a browser might handle malformed input, something with a syntax error, in a particular way. And we would have to know exactly how the browser was going to handle that to be able to apply a policy to say this is allowed or not allowed. And so that made it very hard for us to deal with certain types of challenges. Now this led to my current line of research, which is that I really think we need an interposition layer like this within the browser itself that can talk about what web content can do to your computer, to the DOM, to the file system and network, regardless of what format it is. And that we'll be able to enforce policy regardless of that format type. So this may be not just its interactions with the DOM, but also with the file system and with the network. And we might be able to accomplish this by having these plugins treat the browser like the system call API, at least for some things like the network and file system, and let the browser enforce policies on those actions, rather than going to the operating system directly. OK, so that concludes that portion of the talk as well. Overall, I've shown that there are lots of threats that are on today's web. And this includes both in-flight page changes, where we can end up with changes to a page that a publisher might not want, or that might actually result in bugs and security vulnerabilities. And then web tripwires can help detect when these are happening to help publishers react to these changes. But in the long run, we may need better browser architectures to defeat the other types of threats that we're facing. And we think that this requires clear boundaries between web programs, ways to authorize what's allowed to run within a web program, isolating these programs from each other within the browser, and then enforcing uniform policies on what these programs can do, regardless of content type. So thank you, and I'm happy to take any more questions.
The obvious question, do browser writers care?
Do browser writers care about whether these issues get solved?
Yes.
I would argue that yes. I think as the web is moving more towards an application platform, browser writers are going to be able to sell their browser as being more secure than their competitors, as having a better and safer platform for running code.
What
and
browser
if users
is sold on that feature?
So
when in the course of browser sales has anybody ever cared, apart from the people running links?
So why would browsers be sold in this way? And I think there's a big battle going on right now for market share in browsers. And people want to say that, OK, Firefox has this % market share, and they're doing very well. Now, Firefox certainly sells itself as more secure than IE in many cases. And if they can sell themselves as a safer platform for using your web applications, I think that gives them a good advantage. Or any browser that might happen to show that they have a safer platform. So I think that is a compelling argument.
The same users who install Bonsai Buddy are going to care.
Now, all users may not be educated at this point.
Okay.
That may be much harder. But I think, as we've seen with Firefox, people have convinced their parents and their friends and family that, OK, you should use Firefox. Whether that's an actual improvement in the long run, who knows? But that's certainly a selling point. Yes?
I really like your analogy that the browser becomes an OS essentially. So do you see that as a move towards network computer again? You know, this popular idea sometime, or at least advertised idea some time ago. And the second question is it possible to use VMs to help with some of these problems?
Sure. So the first question was, is this sort of a return to network computing? And in a way, yes. I think that the browser is acting as an operating system, but you're running code now that's some combination of code that's running on the server and code that's running on the client. And we've seen various incarnations of thin clients and mainframes and so on in the past. I think we're just reaching a point in the trends where it makes sense to have some of the computation being done on the client. JavaScript is getting fast enough and so on. But having, say, large data resources like entire mapping databases of the entire world still stored on the server, being able to interact with those. So there's a lot of questions about, OK, how much needs to run on the client and on the server? But there are going to be parts running on the client, and the browser has to do a good job of running those. The second question was, can virtual machines help with some of this? And there was actually a project at UW just before I started work on this project called Tahoma that looked at, OK, could you isolate every web page or web program in its own virtual machine to make sure that it's protected from other web programs and from the client's own computer? And I think one of the challenges that they faced at that time was, OK, again, how do you define a web program? And how do you say what gets to run in a virtual machine? They relied on a manifest that a website would provide that would say, OK, here's exactly what goes into my web program, and this is what runs in the virtual machine. There may also be some overhead issues, but that may be getting better as time goes on.
On the OS history, in this seminar years ago, at least some of the gray beards you may remember, when Netscape gave the first talk, that question came up right at the end. Could or should it be an OS? And so the one hidden, well, it's almost humorous. One hidden reason why they probably didn't push, because they were worried about competing with Microsoft. That was a different issue there. On the other end of the spectrum, I myself, no, I should ask a question. If you turn off JavaScript, does that solve the problem, or it creates other ones?
Sure. I think that some of the safety threats will go away if you turn off all active code in terms of just cross-site scripting attacks and cross-site request forgeries to some degree. Maybe not cross-site request forgeries, but cross-site scripting attacks may be mitigated if you have no active content at all. But I think we're seeing a clear trend on the web where active content is where most sites are headed.
I see that. The point is, I'm actually turning it on and off, literally.
Yes.
I have to recompile a page, and it's a real pain in the neck. And edit the cookies, but I'm getting so annoyed at the flashing stuff all over the place. But if I log into Stanford, I have to turn it back on. So
you're right.
It's a real pain to manage that, but that could be made much easier.
You're right. And it could be made easier to selectively run JavaScript on certain places. There's some Firefox extensions like NoScript that try to help with this. The problem is that it's often associated with, here's a site that I trust to run JavaScript code, and here's a site that I don't. But as we've seen, that doesn't necessarily correlate with whether that site's vulnerable to a cross-site scripting attack or whether they're being affected by in-flight page change.
What I'm saying is I'm doing
yes,
it.
It's
I'm
certainly
very interested in getting a better solution.
I agree. It's certainly an improvement over the current practice. Yes?
I think that the question about whether it should be an operating system is worth following up on even this year. So, what about building support for this
That's
stuff
what I hope. Yes,
directly into the operating system? I mean, is that a sensible direction for people to take?
I think that's a very good question. I think you can try to look at the browser in different ways that really maybe it's just providing a runtime environment that happens to use a HTML renderer and a JavaScript engine as its UI library. And maybe that could get incorporated into the operating system itself. We're seeing some movement towards that in things like Prism and things from Mozilla, Adobe Air. This idea of installing web pages as applications on your own computer makes it much more like something in your operating system. And maybe we do need better principles in the operating system to handle the fact that this isn't a program you've installed. It's actually a principle corresponding to some web program. And that shouldn't have the same access rights as everything else on your computer. And today's operating systems really pretty much treat the user as the only principal when you're interacting with it. So I think that was something that would have to be improved in today's operating system.
If you run each browser window in a separate process, what do those processes need to say to each other?
So that's a good question. The browser processes would ideally not need to say much or anything to each other if these are independent web programs that shouldn't know about each other's existence. Now, in the real world, that's not always the case. You have cases where one website may open another frame and then try to do certain things on the frame to navigate it to other places or access certain parts of it, that it becomes hard. You'd have to allow certain interactions. Now, I think the important part is identifying which pages, that is, which browser windows, belong in the same process and which browser windows belong in different processes. So really, the UI of the browser is orthogonal to what belongs in a web program. You may have multiple tabs that correspond to the same web program, but you may have a page and a frame within it that correspond to different web programs. So the UI doesn't really reflect the process boundaries.
Well, that's what I'm getting at. I'm wondering, I mean, currently you're thinking that you're going to do this by putting everybody who's in the same protection compartment in the same process.
Right.
The question is, would it be better to put each window, and even sub-windows like iframes, in separate processes, assuming you can get the window manager to play ball in aligning the windows, and control the inter-process communication between them through some sort of guard or filter arrangement?
So I think that would be another approach that you could take, that you would have more processes now within the browser, and so there'd be more robustness if one of those crashed. At the same time, we would want some of those checks to be done anyway between pages to say what's allowed to talk to each other. And this process boundary gives us a nice, clear boundary between web programs that is a sort of a defense in depth, if you will. That because we know they're in different processes, we know that they shouldn't be allowed to communicate, even if the browser logic gets something wrong and might otherwise allow two processes to communicate when they shouldn't otherwise. So my goal is to strive for as little communication as possible between these processes so that we know that, OK, that's a clear boundary and it's easy to reason about it.
An example, a secure page, one naively would think that they should be encapsulated.
Sure, an HTTPS page?
Is that correct?
What
are the counterexamples where you may actually implicitly have some communication, or you may want to, or whatever?
OK, so some of the examples that I was referring to are a page could open several frames that are on different sites, or new windows that are on different sites.
A secure page?
A secure page or an insecure page. It matters more on the origin in this particular scenario, where you can do certain things via JavaScript, but not everything. So, for example, if I'm on site A and I open a page to site B, I cannot access the contents of page B's DOM, but I can assign things to its Windows location via JavaScript code. I can traverse some of its frames, for better or worse. And those sorts of interactions you might need to support between different processes.
Part of the reason I'm asking the question is that if you think of this as warfare, then I'd rather have my sergeant sitting at the screen, whatever if I'm in an office. I'm a sergeant at the screen, and what I then want to do is I want to have a tool that supports the sergeant to do whatever he needs to do. So that I tend to call it a human-human computer interface. And at that point, basically, the question, what kind of tools would the sergeant need? So it's sort of basically what you're doing now during the development. But what of that would have to be done dynamically versus what you think you can basically do in your research statically, if you wish?
That's a good question. I'm not quite sure what this sergeant would need.
It's supposed to be a question. I don't think you have an answer yet.
Yeah.
It's a way of formulating the problem, basically.
Exactly.
Do you think that the problem lies with the model that is used for web pages on different sites communicating with each other, or with the implementation of that model within a particular browser? Is it a model problem or is it an assurance problem?
Yes, I think that to a degree this is a model problem. That it's hard, that the origins just are not providing us the boundaries that we want, and that we would like a different model if we're defining what a program is. There's certainly bugs in the way it's implemented today, and those are coming up in papers frequently. But I think even if you fixed all of those, you might still want different sorts of boundaries between programs.
So I feel like the line between active code and data on the web is a little bit fuzzy. And you sort of talked about this earlier with, well, it's not just JavaScript code that needs to be authorized, but also Flash. And I was wondering just like how far you might go down that line of thinking, because it seems like iframes, for example, could be considered a form of active code. Forms, password fields. There's lots of things that you might want to worry about having injected into your page as part of a cross-site scripting attack. Even if no JavaScript code runs, the attacker might still be able to trick the user into entering their password. Do you think that the authorized code approach can be used to authorize the entire page and all of its web features, or is that just going to be impossible?
So I think that's a great question. I think that there is a distinction between, say, active code and data or passive code or whatever you want to call it, but that may still be sensitive. So you may, as you say, it may inject a password form or try and get other things. And so the rest of the page's integrity does matter. I do think that it makes sense to have mechanisms to support integrity for an entire page. I don't know if that's going to be as easy to deploy as something where the browser looks for, okay, at least here are some aspects of the page we know, here's the scripts that we know are allowed to be there. And I think that the trade-off there is, okay, how much of the page is dynamically generated and how much do we know in advance? So if the active code is something we know in advance, it might be easier to generate a whitelist for it, whereas some parts of the page are generated on the fly. It might be harder to say, here's the known good copy of it. If we can get integrity for all of that, I think that's a very important goal.
You can at least protect the hard drive and file systems.
That's right. In terms of what happens as a consequence of running this, what happens to the hard drive and file system is a big thing, and the network as well.
A little more general, again, as a concept more than as more a question and answer. Think of undo. Let's say you happily cruise and suddenly you find something you don't like I have this flashing problem because I'm slightly dyslexic. But you might suddenly find that something's deleted that shouldn't have been. At that point you know that something went wrong, but now it's sort of too late, right? So in some sense you want to be able to back up. Backtrace basically to the decision point where something went wrong, and at that point you can sort of figure out, put the right switch and go forward again. So in some sense you want infinite undo, which we all know we can't have. It's again as a concept. So that's
yes.
Usually it's too late. And then you have to back off or wait till you can buy a better product or whatever.
The web makes that undo problem a bit harder too, because as long as it's confined to your own world, if you're just working in your word processor, then you can undo it because those changes haven't been seen by anyone else. But
also I'll look at the virtual problem the same way.
Sure, exactly.
Because at some point you have to get in and out, but that's the decision point or something where you have to commit basically.
Right. Okay. Thank you.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.